and welcome to this workshop on transforming your application with MicroProfile Reactive Messaging. I'll be leading this workshop today, and my name is Grace Jansen, and I'm a developer advocate at IBM in the UK, if you can tell from my accent. My Twitter handle is up there, so if you'd like to give me a follow, if you'd like to tweet me, if you want to tweet any of the slides from this session, please do use my handle there. It's at GraceJansen27. So, why do we need this workshop? Why do we need our applications to go through this transformation? What's happening that sort of this range of reactive APIs and frameworks and toolkits are suddenly coming to the forefront of application modernization and application design? Well, our application landscape is really rapidly changing. So we've got this exponential growth in data that our applications now have to deal with. In just 8 years' time, the average person will interact with a connected device nearly 4,800 times per day. And you can see here just the pure volume of data created worldwide is increasing at an exponential rate. And our applications are having to deal with this exponential growth in data. Suddenly they're having to deal with huge volumes of data that we just didn't have to when we first started designing them. Not only that though, the load to our system, whether that's the amount of data our system has to sort of computate or process, or whether that's the number of users trying to hit our system, trying to access the web pages or applications that we built, that load to our system fluctuates hugely depending on the time of day of the week during the month of the year, the season. It all depends on various factors, and our applications have to be able to scale to these fluctuating load volumes sort of dynamically. And not only that, but society now has this increased expectations of what applications should be like. Users don't expect applications to go down or to fail unexpectedly. They don't expect applications to lose items in their basket or to suddenly just pop them up a 404. So what does this actually mean for our applications? Well, it can feel a bit like this. It can feel a bit out of control, chaotic. Our applications are having to deal with a huge amount of fluctuating load, increasing data, increased expectations. So how do we meet these rising demands that society places on us, and how do we evolve our application architecture so that we can best deal with these new and sort of interesting demands and sort of issues and problems? So the first step we took towards sort of moving in the direction of evolving our applications to better deal with this new landscape is evolving the infrastructure that we're running our applications on. So what used to be single cores, well, now we can take advantage of multiple threading and multiple cores. We can now utilize cloud infrastructure. We can virtualize all of our applications, and we can use containerization within our application architecture. So what we've done is we've taken it from sort of what was originally in sort of data servers, in data centers, and locally stored. We're able to distribute to multiple different data centers, utilize infrastructure that we just would never have had the opportunity to before in a distributed manner, so that we can have this sort of immediate response from applications. And not only that, we've also evolved our application architecture. We've evolved it, but I think there's a step further we can maybe take it. So we've evolved it from this monolithic application, which was fine at the beginning of application architecture, because our applications were fairly small, there wasn't that much data going through them, but we've evolved from that into microservices, which was a great step forward. Microservices allowed us to sort of isolate failures and bugs easier, to install new features easier without having to tear down the entire application and bring it back up again. It also allows us to sort of dynamically increase the number of microservices for a particular service or a particular part of our application, depending on the load to that system. So microservices was a great leap forward. But where do we take it next? How do we still improve upon this application architecture to take as much advantage as possible from the underlying infrastructure that we've developed in order to deal with this increase in data, this fluctuating load, and these increased expectations from our applications, from society? So this is where reactive comes into play. So reactive is based upon sort of, in essence, this manifesto that was designed back in 2013, and it details, this manifesto is basically a specification that details out the behaviours, 4 key behaviours that we want to see in reactive applications. Applications that can react to their surroundings, react to events, and react to the users using them. So the first underlying behavior that we need to see in reactive applications is having this message-driven asynchronous backbone. So this asynchronicity allows us to really decouple the aspects of our application, the different components that we have in our applications, so that we can sort of prevent potential failure points, prevent bottlenecks, and enable sort of efficient use of the underlying infrastructure within our system. So having this asynchronous message-driven backbone is really important. Building on top of that, we have elasticity. So that sort of relates to what I was talking about before, being able to dynamically scale our resources both up and down depending on the fluctuating load to our system. Being able to gracefully handle those load fluctuations without our system sort of collapsing or failing or becoming unresponsive. Another feature, another characteristic or behavior that our message-driven underlying asynchronous backbone allows is this resiliency. So now that we've decoupled the components of our application in its communication, we can start to build in resiliency into our application. Now, resiliency is arguably probably the most important characteristic here in this manifesto. And that's because if we don't build in resiliency to our application, to our system, and it fails and crashes, there is no system, there is no application up for the user to be responsive. So it's really important that we build in that inbuilt resiliency. And that's because as much as we might try, as software developers, we cannot predict every potential failure that might happen to our application. So what we need to do is gracefully deal with potential failure points and potential sort of catastrophic events by inbuilding resiliency into our application. And these three characteristics lead to the last characteristic in the Reactive Manifesto, and that's responsiveness. So being as responsive as possible to state changes, to events, to messages, to any sort of state change within the system. So that could be clicks on a website, that could be sensor data from IoT sensors, it could just be the processing of an event that happened previously, which causes another event. So by being responsive, we can react and be reactive. So responsive is sort of the culmination of the rest of the characteristics within the manifesto. So by implementing each of these characteristics, we can then create truly reactive and non-blocking applications. But how do we put this sort of higher level characteristics into practice when we're building applications? So how do we make a highly responsive app? Well, there are different layers that we need to think about in our own application when we're designing reactive applications. So here is a basic application. It's only got 3 microservices, but it's just to give you an idea of the various levels we need to consider. So there's obviously the data level, which depending on your application, might have an asynchronous message-driven backbone already. For example, you might be using Kafka or MQ. And those tools help to enable that asynchronicity and that non-blocking at the data level. But our applications are made up of just more than just data. We have microservices, we have logic, we have processing to do within them. So what can we do inside our applications to really enable that asynchronous non-blocking behavior that we want to see in reactive applications? So the first level I'm going to talk about is inside the microservices themselves. So we need to be considering the logic flow within our microservices. And that's where we can utilize this sort of paradigm of reactive programming patterns. And within reactive programming patterns, we can put into place things like futures, reactive streams, or reactive programming libraries. So what do I mean by reactive programming? Here's a basic definition. So reactive programming is all about this asynchronous programming model. So it's about driving forward the logic within a microservice via the availability of new information instead of by a thread of execution. So it's all about introducing this asynchronous nature into the logic flow within the programming in our individual microservices. So how do we achieve that? Like I said, there are several patterns that you can sort of put into place to achieve this. One of which, if you're familiar with Java programming, you're probably familiar with already, which is futures. So futures are essentially a promise to hold the result of some operation until that operation completes. So all about asynchronicity there. We've also got things like reactive programming libraries. So they're all about composing asynchronous and event-based programs. And examples include RxJava, which is used by many of the reactive frameworks and toolkits that exist today, And there's also small-r mutiny. Again, another open source library you can use. And then we've got reactive stream specification. Now the reactive stream specification we'll go into in a bit more detail later, but essentially, as a sort of summary, it's a programming concept for handling those asynchronous data streams in a non-blocking manner while providing important back pressure to our application, which again we'll go into in a bit more detail later. So we've looked at inside the microservices. We can see how we can put these patterns into place to enable more asynchronicity and more non-blocking behavior within the logic of our microservices. But there's more to our application than just inside the microservices. So we need to think about sort of scaling out a bit, looking at the bigger picture of, okay, we have our application, we have our system, but we have components within it, microservices, and although they individually might be reactive, we have to think about how they also communicate with each other. So how do the various components of my application communicate together and communicate to external components, maybe an external database or messaging broker or another third-party application? And so to make this as non-blocking and as asynchronous as possible, we can implement these things called reactive architecture patterns. So this isn't an extensive list of reactive architecture patterns. If it was, we'd be here all day, but this is just some of the 4 sort of commonly used patterns that we see often in application architecture, specifically in reactive applications. So the first one is CQRS, so that stands for Command Query Responsibility Segregation, and that's all about sort of, when you boil it down, it's all about splitting out the read and the write APIs within an application to make the availability of data greater, so enabling that high availability that we want within reactive applications. Then we've got event sourcing, so you might sort of hear about event sourcing a lot when looking at things like messaging brokers or sort of open source projects like Apache Kafka. So event sourcing is all about persisting the state of a business entity, like an order or a customer within an application, as a sequence of state-changing events. So whenever the state of a business entity, so that customer or that order, changes, a new event is appended to the list of events. So in the case of Kafka, for example, there's an immutable event log, and you can add new events to that log, to the end of that log, as that state change of that entity changes over time. Then we've got back pressure. So back pressure is one I mentioned with reactive stream specification, and it's a really great reactive architecture pattern that is introduced when you utilize the reactive stream specification and many of the reactive toolkits and frameworks that are available for you to use. So back pressure is a feedback mechanism that works from a downstream component to an upstream component. So it's a way for a downstream component to provide feedback back to the upstream component to help control the rate of flow of records or messages or events flowing down through the various components downstream. And that's to make sure that the downstream component doesn't become overwhelmed or become a potential bottleneck or a potential point of failure within the application. So by providing this feedback, we can ensure that we're not overloading our downstream components without knowing. So then we can also change the rate of flow so that we can make sure they have enough time to recover and we have a fully functioning responsive application. And then we have circuit breaking. So circuit breaking is sort of, if you've ever done electrical engineering, really similar concept. So circuit breaking in this case is when we have a downstream component who maybe is under extreme stress or load or stuck in a particular process, and they might produce a particular failure message over and over and over again in their logs. And a parental component or a parental microservice, for example, might be able to pick up on this continuous repeated failure and realize that that application is under extreme stress or load. And so what it will do is it will temporarily stop requests or stop the messages or events or data being flowed into that application, and instead it will reroute it to, let's say, replica microservices to give that component a chance to recover, to get through that process, to come back online. And once it does get better and it's back to its healthy, normal self, the upstream component then can reinstantiate that route back to that component and again send it through requests once more, or data or events or messages. So they're just some of the reactive architecture patterns you can put in place when you're creating reactive applications. So we've looked at sort of the data layer and what tools we can use. We've looked at the microservices layer and the fact that we can implement reactive programming within that. And we've looked at sort of the wider picture, the system level, and looked at the different architecture patterns we can put in place. But are you expected to go and do this yourself? not entirely. We're not expecting you to create an entire sort of set of APIs and libraries and toolkits. Instead, there's a whole open source reactive community on hand to help. So as I mentioned before, there's something called the Reactive Streams specification, which was made by the community. So it was an initiative started in 2013 with various different companies like Netflix, Pivotal, Lightbend, etc. And the Reactive Streams working group released this API for several languages, including Java. And this API is essentially providing a standard for asynchronous stream processing with non-blocking backpressure. So it's composed of 4 different interfaces, and you can visit our article here to find out some more information on those. But essentially, what it is it provides a subscription, a publisher, a subscriber, and a processor. And it's that subscriber there that provides the backpressure that we need when we're creating reactive applications. And the reactive stream specification is a specification used by many of the reactive toolkits and frameworks that are available. So what reactive frameworks and toolkits are available? So these are some of the open source reactive toolkits and frameworks that you can utilize when you're building reactive applications. And they help to enable things like asynchronous programming, so that reactive programming that I was talking about. And also some of the architecture patterns that we saw, like backpressure or event sourcing, for example. So we've got Vertex, which is sort of slightly different in that it utilizes a concept called verticals, and it introduces this event-driven, this distributed event bus within it. So it's really focused on putting events at the heart of the system, and that is, again, these are all open source. Then we've got Akka, Play, and Lagom. These are a set of 3 sort of frameworks that work together, but they're based off something called the actor-based framework. So slightly different to microservices. If you're already using actors within your microservice, Akka is definitely a framework that I'd look at. But if you're not already using actors, it can be a little bit of a paradigm or shift to get your head around, because it's not always a one-to-one matching between actors and microservices. The actors tend to have mailboxes and they communicate by sending messages between their mailboxes, but they also have a hierarchical system of having parental actors and child actors. So a slightly different system, takes a little bit to get your head around, but definitely something to check out. And they all work together to provide reactive, sort of an end-to-end reactive solution. Then we've got RxJava, which is sort of mostly a tool for building for introducing that reactive programming into your application. We've got Project Reactor, which was initially started by Spring, but is again an open source project. So if you're interested in sort of Spring Webflux, for example, utilizes Project Reactor within it. So that's another open source framework. But the one we're going to be focusing on today, that we want to sort of put into practice and get hands-on with, is MicroProfile's reactive offerings. So it's reactive messaging APIs. So let's take a look at Reactive and Eclipse MicroProfile. So for those of you who've not come across MicroProfile before, Eclipse MicroProfile is an open source community specification for enterprise Java microservices. So it's really all about sort of providing APIs and specifications that you might need if you're using enterprise Java but want to be building a microservices-based application or system. And as we said, it's a community specification. So the development of this specification has been driven by a huge array of individuals, organizations, and vendors. So it's really being created by the community for the community. So you can see here there's a huge array of sort of contributors, and you can see all of this information on the eclipse.org website, and it's updated. This is the sort of contributions from the last 3 months to the MicroProfile projects. So let's take a look at what MicroProfile offers us. So here is the MicroProfile 3.3 stack. The 4.0 stack is in pre-release stage, so if you want to go and check that out, you can check that out on the MicroProfile GitHub page. But at the moment, this is the only sort of in production, this is the latest sort of in production stack for MicroProfile. So at the bottom, you can see this sort of triangle shape, which is the core APIs that come with MicroProfile stack. And on the right-hand side, you can see these sort of, this L shape on its side, which is the standalone projects that are that are built by the MicroProfile community, but they don't come as standard as yet in the MicroProfile stack. So in those standalone projects, you can see Reactive Messaging 1.0, and that's the one we're going to be focusing on today. So the role of this specification is to deliver a way to build systems of microservices, promoting both location transparency and temporal decoupling really enforcing this asynchronous communication between the different parts of the system. So this is sort of MicroProfile's answer to how to introduce reactivity and asynchronicity and non-blocking behavior into your application. So it aims to deliver applications embracing the characteristics of reactive systems, which is exactly what we're looking for. Now, the Reactive Messaging 1.0 specification is actually based on two of the other specifications that I've mentioned. So one is that reactive stream specification, which is that community specification that was made back in 2013. But it's also based on the Reactive Streams Operators 1.1 specification, which is a MicroProfile standalone project. So the Reactive Streams Operators specification is a MicroProfile specification which builds on reactive streams to provide a set of basic operators to link different reactive components together and to perform processing on the data which passes between them. But we won't be using Reactive Streams Operators directly, we'll be going through the Reactive Messaging 1.0 specification. So, how does the Reactive Messaging specification work? So, most applications using reactive messaging are composed of CDI beans that consume, produce, and process messages. So these messages can either be wholly internal to the application, or they can be sent and received via different messaging brokers, like Apache Kafka or MQ, for example. So when we're looking at MicroProfile Reactive Messaging, we can utilize these annotations that it introduces. And these annotations sort of apply to the application's beans. So there's two applications we can use, which is at incoming and at outgoing. So the at incoming represents sort of events coming into the bean or the particular microservice, and the at outgoing represents data or events or messages going from sort of it being a publisher, so going from that particular method or particular microservice out to another. So the annotated methods at incoming and at outgoing are connected by named channels. Now a channel is just an opaque string. So in this case, at the bottom of our diagram of our slide here is a diagram that shows that method A is connected to method B by this channel called order. So we can see here how method A's at outgoing annotation has order within it, and it's connected to the at incoming order on method B by that channel order. So they're matched up by these channel names. So when you use MicroProfile Reactive Messaging annotations, so that at incoming and at outgoing, sort of vendor implementations like OpenLiberty as an example, creates a reactive streams component for each method and joins them up by matching these channel names. So that's where the reactive streams component sort of comes into play. You can also have methods or microservices that have both at incoming and at outgoing, like method B does. This represents a processor. So it's not just a publisher, it's not just a sort of a consumer, but it does both. So it processes some form of data and republishes that back out to another channel. Now there are two types of channels that we need to be considering. There are internal channels and there are external channels. So external channels are managed by connectors, and you can have connectors to many different sort of external messaging brokers, for example, like Apache Kafka. So reactive messaging connectors are extensions managing the communication with a specific transport technology. So with OpenLiberty, we have the OpenLiberty Kafka connector, which we'll be utilizing in the interactive labs. So talking of the interactive labs, we'll get on to sort of what we'll be doing in this workshop and the hands-on component of it. So we'll be utilizing this online environment called Skills Network Labs. So this is an environment that's been made by IBM. So if you guys have any suggestions, we're constantly trying to work on the site. So please do let me know if you guys have any suggestions or run into any issues, and we can try and sort that out for next time. But this sort of online environment means that you don't have to download any prerequisites, you don't have to download anything onto your computer, which makes it a lot easier for you guys to get hands-on with new tech without sort of clogging up your machine or having to get permissions if, for example, you're not allowed to download particular software or technology onto your local machine. So the labs that we're going to be doing today, we're going to try and get through 4 of these modules. There is a 5th one. If you do have time and you get onto that, feel free to go ahead and do that. If, for example, there are also additional modules. So if, for example, you wanted to take a look at sort of asynchronous communication without the reactive component, or look at how we can push this reactive application to something like OpenShift, we have modules like that available. If you just scroll down this link, if you go to this link, you'll find the page for all of the labs. And if you scroll down, you'll see the additional labs that you can go and take either in your own time, or if you speed through these labs and want to do it during this session, feel free to, absolutely fine. But today we're going to try and do Module 1, Module 2, Module 3 and Module 4. So I'll give everyone a little bit of time just to type in that link. So it's https://ibm.biz/reactive-java-labs. So that's the URL you want to hit, and that will be available after this session. So if you don't get through it all, or you have to drop off for any reason, that's absolutely fine. You can reach these labs afterwards and continue them at your own pace. So without further ado, we're going to move on to Module 1, Creating Reactive Java Microservices. So the application we're going to be using within all of these modules and all of these labs is the same application. So that hopefully this will make it easier for you to follow through all of the labs and sort of not have to worry about the underlying application, but focus more on the new technologies and the reactive sort of MicroProfile messaging specification and the technologies we'll put into place, so you can focus on those. So this application that we'll be using is made up of two microservices. So we've got the system microservice and the inventory microservice, and you can see the basic sort of broken down application architecture on the right hand side here in the diagram. So in the system microservice, we've implemented logic there which says that basically every 15 seconds the system microservice is going to calculate and publish an event that contains its current average system load. And then in the inventory microservice, we're then subscribing to that information, in this case from sort of our Kafka broker that we're using, so that it can keep an updated list of all of the systems and their current system loads. And if you wanted to access the sort of current inventory of the system, you can access that via the /systems REST endpoint, which we'll be doing in some of our labs later on. So, what are our aims for Module 1? Well, in Module 1, we're going to be looking at how we build reactive microservices that are able to send requests to other microservices and asynchronously receive and process those requests. So really introducing those asynchronous concepts through using the MicroProfile Reactive Messaging specification, which leads me on to sort of the second aim. So the second aim is going to be learning how to utilize reactive MicroProfile Reactive Messaging to write and configure the application to send, receive and process events efficiently. And the third aim is to learn how to connect the reactive application that we're building using sort of the connectors we have available in the reactive, through the reactive messaging specification to an external messaging broker. In this case, we'll be utilizing Apache Kafka. So let's take a look at the lab itself. So here is the landing page for the Reactive Java workshop we're going to be doing today. And this is on the Skills Network site that I mentioned. So these are the sort of 5 modules you can do, and you can see here are the additional modules at the bottom if you'd like to do them, and some more useful links leading on from these labs for you to take a look at afterwards. So the first module we're going to do today is this module here, Module 1, which is creating reactive Java microservices. So you'll need to click into that. It will ask you to sign in and ask you about this. So just click I accept, and then you can log in with any of these. Now I'm going to log in with Cognitive Class, and I'm going to log in with my IBM ID, but you can log in with any of these different social logins if you'd like to, or you can create an account if you'd like to do that as well. So I'll give you a few minutes just to get signed in and logged in to this environment. So you might just need to give it a little bit of time. It will show sort of a loading bar with this sort of term, your server is starting up. When your server does start up, you should see an environment like the one I'm showing here. So you should see on the right hand side this sort of empty IDE that we're using, and on the left hand side the instructions that we'll be going through. Now that you're in this environment, what I want you to do first is go to Terminal, then go to New Terminal so that we can open up this terminal and start typing in our commands here. So I'll give you guys a few minutes just to get started with that. Now, because we've gone through sort of what this application is and gone through a lot of the sort of theory behind asynchronicity, behind reactive and microservices, we're just going to go ahead and skip this first step in the instructions because it's basically just talking about what you'll learn. It's talking about asynchronous messaging and why you might want to go down the asynchronous route, why it's beneficial, the advantages you can gain, what reactive microprofile messaging is, and sort of what the application that we'll be using is, and what you'll be creating. So we'll just continue by clicking this big continue button at the bottom. This is the same for all the instructions. You just click the continue button and it will take you to the next step. So as I said, the first step is to go terminal and then open that new terminal using the IDE on the right hand side. So let's check that we're in the home directory by using pwd. Now this button in the corner allows you to copy, so you can just click that and then you can paste it straight into the terminal at the bottom. You'll have to click first before you can do any shortcuts or right click and paste. Just because it will think you're on the instructions otherwise, so you won't be able to paste. So make sure you click first in the terminal at the bottom and then paste. Cool, so that's all working. So we're just going to clone our repo that we need first. So get on with cloning that and cd into the directory guide-microprofile-reactive-messaging. Now we're going to be using the start directory. There are two directories within this folder, so let me show you. So we've got the start directory here and we've got the finish directory here. So the finish directory is actually basically the entire lab complete. So if you wanted to check out what your application should look like at the end of this lab, at the end of these exercises, head straight to the finish directory, but we're going to be working on the start directory. So that's why we're just going to go straight into the start directory, cd into it. So now that we've navigated to the start directory, we can actually begin doing all the instructions that we need to convert our application to use reactive messaging from the MicroProfile specification. So the system microservice is a producer of the messages that are published to the Kafka messaging system as a stream of events. Like we said before, that system microservice is sending an event every 15 seconds of the CPU usage from the last minute. So what we need to do is we need to create a system service class. So using this command here, it should create it for us. And that means all we need to do is go to File, Open, head to Guide MicroProfile Reactive Messaging, like we said, and straight into Start, because that's the directory we'll be using. And then we want to go to System, src, and then into Main, Java, IO, Open Liberty, Guides, System, and there's that system service.java that we just created. So when we open that up, it should be blank, as it is. But we've got all that we need here that we can just copy straight in. So let's go ahead, copy that, and paste it into this system here, into the IDE. So you can see here that in our system service Java, we've got a few imports. And you can see that we've got things like the RX Java library here that we'll need. We've got the reactive streams specification and that reactive messaging specification import. Now, specifically for the system service, because the system service is the one publishing events and not consuming them, we're using the outgoing annotation that I mentioned in the presentation. And you can see that outgoing annotation used here. You can see that we're using the topic called system load. So when we do the inventory microservice, when we take a look at that in a minute, we should see that we're consuming from the same topic. So we're consuming from that channel that we're using, because in microservice reactive messaging, like I mentioned, the outgoing annotation and the incoming are connected by these named channels. So we're using the system load channel. And we're using this sort of flowable interval, which is a method from RX Java. So it was introduced in RX Java 2.0, and it's designed to essentially be a version of sort of the observable method that you might be familiar with if you've used RX Java 1.0, but flowable offers back pressure on top of that, which you don't get with observable. So we're using the flowable interval to essentially send out an event every 15 seconds. So you can see here we're sending it out, and it's getting the average system load over the last minute. So that should be essentially our system service.java file that we need to create. So we'll continue on, and we'll take a look at the inventory resource class we need to make. So now we need to make the matching inventory class. So if we copy this command again and paste it into our terminal, and then we head again to File, Open, we go to Guide MicroProfile again to Start, but this time instead of to System, we're going to go to Inventory. So still src, Main, all the rest should be the same, Java, IO, Open Liberty, Guides, and now Inventory, and we should see Inventory Resource, the class we just created, just here. So we'll open it and it will be blank. Fantastic. So if you go down to the bottom of this file here on the left-hand side in the instructions, and copy it and paste it in. Again, we've got a few sort of imports here. So this time we're importing the incoming annotation from the reactive messaging specification, which you can see there. So if we take a look at this inventory resource class. So you can see here, these are just some of the methods that we're using to make sure we've got the correct sort of host names, that we're replacing the data and deleting the previous data, for example. You can see here deleting, but the one that we're interested in is this @incoming annotation. So this is the reactive messaging specification annotation we're using, and because the inventory microservice is consuming those sort of events from the Kafka topic, and we're using the @incoming annotation, and we're connecting to the system load channel. That's how we can match up that outgoing and @incoming. And then you can see here that essentially we're just getting the information and updating the system. So if we continue on. So as I was mentioning, the system and the inventory services exchange messages via the external messaging system through channels. Remember, there's a difference between the internal and the external channels. An external channel is controlled by and managed by a connector. So in this case, we're using a connector to connect to Kafka. Because this was all based on OpenLiberty, which is an open source web application server. Check it out if you haven't already checked it out. You can go to openliberty.io, a great site where all of these guides and these labs originally came from. So because we're using OpenLiberty, we're going to be using the OpenLiberty Kafka connector within this application. So it makes it easier to connect each service to the channel. So we just need to add in some current configuration keys in a properties file for each of these services to be able to define sort of the names of the channels and the topic in the Kafka messaging system. So we can match up the channels to the Kafka topics for both the system service and the inventory resource classes. So as I said, the OpenLiberty includes the Liberty Kafka connector for sending and receiving messages from Apache Kafka. So that's the messaging broker we're going to be using today. So the system and inventory microservices each have a MicroProfile config properties file to define the properties of their outgoing and incoming streams. So if you haven't checked out MicroProfile config, we have a guide on the OpenLiberty website. So if you go to openliberty.io and head to the guides section, you can find all of our amazing guides here. They're usually between 15 and 30 minutes, and you should be able to find one on config. You can even search. So configuring microservices, for example, will teach you all about an introduction to MicroProfile config, which is another specification within the MicroProfile stack. So we're going to be using that MicroProfile config specification to define the properties we need for the outgoing and the incoming streams. So we need to make this properties file first. So copy that command and paste it into our terminal. Now we need to go to File, Open, again, Guide MicroProfile and Start. This time we're going into the system to edit that first. So src, resource main, and then resources this time instead of Java. Then we're going into meta-inf and we're going straight to the MicroProfile config properties file we just made. So open that and it should be empty, fantastic. And now we're going to copy in the configuration properties that we need. So you can see here that we're defining the connector is going to be Liberty Kafka. That's the one we're using, which is OpenLiberty's connected to Apache Kafka. The topic that we're going to be linking to is the system load topic. And you can see here we've got serializers to convert between them. So that's what we need for sort of the system microservice. So now we're going to go to the inventory microservice, which again uses a similar MicroProfile config properties configuration file. So we need to make that. So if we copy this and paste it into our terminal again, fantastic. So now we've made that file. Let's go open it. So open, guide MicroProfile, start, inventory, and then into src, main, resources, meta-inf, and straight into that MicroProfile config properties here. So again, this is empty, which shows that it's the correct file. So let's copy this and paste it into here. This time, again, notice that we've got the system load here and the Liberty Kafka here. Now, because this is we're using Apache Kafka, and because this is a consumer, we do have a group ID here at the bottom, which is the system load status. So let's continue. So now we need to configure the server. So to be able to run these services, the OpenLiberty server on which all of these services are running needs to be correctly configured. So we need to include the MicroProfile Reactive Messaging feature within it to enable all of these configuration properties and the methods that we've got inside the different classes in our system and inventory microservices. So we need to create a server.xml configuration file. So let's copy this command in to make it easier for us. And then we'll go to File, Open. Please remember when you are making these files to save as you go along. I've been automatically saving, but I should point that out. Please make sure you have saved all your files, or when we build this application, nothing is going to be built. So let's go to Guide, MicroProfile Reactive Messaging. Again, still to start. We're going to go into System, SRC, Main, and then Liberty this time, and then into Config, and there's that server XML that we want to edit. Again, it's empty, which is a good sign because we just made the file. So if we copy in this and paste, and again save, you can see here that we've introduced the feature of MicroProfile Reactive Messaging, and above you can see some of the others that we've used. So we've used MicroProfile Health and MicroProfile Config. And you can check out guides on our Open Liberty website if you'd like some more information on those, or like to get hands-on with them if you've not before. Cool, so let's continue on. So this server configuration file is already configured for the inventory microservice. So we don't need to do the server.xml for the inventory because we've already got it in the directory. This was just to show you sort of what we need to import for each. Okay, so now we need to get on with building and running our application. Now that we've put all of these sort of methods in, we've got the configurations, we've created our server.xml files. So now we need to create the Maven configuration files. We need to create our pom.xml. So let's add this into the terminal, and then we want to open it so that we can edit it. So open, guide MicroProfile, start again, and this time just system, and it should be there. Now watch it with this one because this is the pom.xml you want to open. There is a couple of projects, a couple of sort of lines down. That's not the one you want to open. It's this one further up within the SRC, within the system file, sort of directory. So let's open that up. You should know if it's the correct pom.xml you've opened because again, it should be empty because we have just created it. So let's copy and paste all of this in, all of our dependencies. So here we put in some comments to help you hopefully understand each of the sort of dependency groups that we put in. So you can see here that we've introduced the dependency for RxJava, which we've been utilizing to, to send out that event from the system microservice every 15 seconds. Then we've got the Apache Kafka, which we need for our intermediary message broker that we're using. And then we've got the Eclipse MicroProfile dependency for the reactive messaging specification here. Fantastic, so now that we've got that, make sure I save. So now we want to go ahead and start our Docker environment. We have provided all the Docker files you'll need to get started. So all we need to do is copy these commands to run Maven and to install and package the goals from the command line in the start directory. So let's paste those in and have a look. And that last command, that Maven package, just to get everything packaged up and ready to go. So it's all looking good so far. Hopefully you're seeing similar output to what you're seeing here on my screen. Fantastic, build success, that's what we want to see. So we're going to run the following command just to make sure we've downloaded the latest Open Liberty Docker image and the required images for Kafka. So if we just copy that command, we built these scripts hopefully to make it easier for you. But I mean, feel free to hand type them and hand select the version you'd like if you want to. This is the one we're going to use. So we're just on the second one here. So we're pulling Kafka right now, and we will need to pull Zookeeper. So when we're building applications that are using Kafka at the moment, you still need to deploy Zookeeper just for that metadata. In future versions of Kafka, they have planned to have that as a separate topic within Kafka. So you shouldn't need to have Zookeeper, but right now it is still needed. Fantastic, so we've run all of those Docker commands. So now we're going to run the commands to containerize the microservices and build our system. These are the exciting ones, see if it works. So again, just copy that command in and paste it into your system, and then run that second command for the inventory service. So now we're going to use the provided scripts that we provided within the sort of application code to start the application in Docker containers. The script creates a network for the containers to communicate with each other, but it also creates those important containers for Kafka, Zookeeper, and the microservices in the project. So just for simplicity's sake, we've only started one system service. Now, if you want to sort of go off in your own time and run multiple system services, feel free, and it will show more when you sort of run the curl commands we're going to be running. It will show more than just one system and its data. But right now, we're just going to run one. And then we're going to continue on because that's created. So after the application is up and running, you can access the application by making a GET request to the /systems endpoint of the inventory service. So like I mentioned back in the presentation, that's how we're going to see the latest output of the CPU usage within the last minute. So that one gets updated. So if we copy and paste this curl command, now you might need to wait a little while just to make sure the application is actually definitely up and running. We'll try this now. It might not work. We'll see. Fantastic. So my system's being quick today. So I've got the correct output, which is giving me a host name and giving me that system load data, which in this case is 1.97. So you can see here, we've got an example on the left-hand side in the instructions of what you should see. And I'm seeing the same sort of output in my own application on the right-hand side in my terminal. So you can revisit this URL after a while, and you should notice that the CPU system load property for the systems change. So if I now re-input the same curl command, you can see here how my system load has actually changed, depending on just what's going on in my system. So you can see here, I've still got the same host name because it is still the same system service that we deployed, but you can see that the system load itself has changed over time. And you can keep doing that as long as you like. Each time it should change, you should see a difference. So you can see that this really is changing over time. You can also see, so for example, if you've set up multiple system services, you've got multiple systems running, you can actually search for a specific host name by using this curl command and entering the host name that you want to look up. We've only got run running at the moment, so I'd only be able to do it with that one. So we're not going to do that one for just now. So we have successfully created a reactive application that's based off two microservices, and we connected them using Apache Kafka and implementing the MicroProfile Reactive Messaging specification. We've used RxJava as well within there, and we've been using the incoming and outgoing annotations. We've taken a look at how we set up the correct configuration for those in both the server.xml and the POM files to enable the correct dependencies that we need. And we've been able to test that by testing that our service does produce what we were expecting, which is we were able to get our system service to publish that event of its latest system load to Kafka, and we were able to consume that in the inventory service and expose that as a REST endpoint via the /systems endpoint in the inventory service. So we've shown that from end to end, we've been able to successfully create a reactive application. So now what we're going to do is tear down the environment, because this particular online environment that we've created actually saves your progress. So for example, if I was to refresh your application accidentally or go out of it, your progress will be saved. So although this jumps back to step 1, you can see here on the right hand side when it loads that my application is actually all still there and back where I was before. So you can see here, I can do the same command, it saves all my history. And you can see here that I'm just back to where I was. So don't panic if you accidentally quit or accidentally refresh. That's absolutely fine. It will save your progress. But what that does mean is that we do, at the end of each lab, have to sort of clean up our environment afterwards. So if we do a stop containers to make sure our Docker containers stop for us, and then if we continue on, so they're just stopping. And then what we need to do is delete the directories and the code within it, so that when we download the next one, we're not confused between them. So now that the sort of containers have stopped, we can go ahead and delete those directories. Fab! So that's the end of module 1. Now we're going to move on to module 2. So for module 2, like any good developer, we need to introduce tests into our application because we developed something and now we need to test that it works. So why do we even write automated tests? Is it because our bosses or our team leads tell us that we need to have a certain amount of coverage? Is it because we just love writing tests? Probably not. If we were all perfect developers, we would just write the code, push it up, and deploy it immediately into production on a Friday afternoon. And we wouldn't get calls at 2 a.m. for support. But unfortunately, we aren't perfect developers. And even if we are perfect developers ourselves, most of our projects involve a huge variety of individuals. They might even be open source, and code can sneak in that we need to introduce tests for to make sure that we're not sort of creating bugs or creating problems that we're going to need to fix later. So we have to write tests. And that's so that we have the confidence that our applications work in the way that we want them to. So we want to make sure that our applications are working correctly. And that's why tests are so important. So what are the different types of testing that we can introduce into software development? Well, we've got unit testing, which most everyone will be familiar with in the software world. We've got integration testing, and we've got system and UI testing. So, and most of the time, a combination of all of these is important if we want to achieve sort of an application that's really testing every aspect of it. But in reality, what do we really have time to do? What do we really get done? Unit testing is fairly easy, and we can do it pretty much right away once we've written the code, because it's there, we can write it, we know what code we're testing. But integration testing and system testing tend to be harder to fit in. In fact, system testing tends to be a manual test rather than an automated test, and that's if you have time and remember to do it. But the problem with just doing unit tests is you get sort of scenarios like this on the picture here. So our unit tests, does the tap turn on? Does the tap turn off? Does the drain work? And does the sink not overflow? All pass. But if a plumber came in and installed that into your house, you wouldn't be very happy because it's not working the way it was meant to. It's not working as it was designed to, and the customer isn't satisfied with the way that it's been sort of put into production, as you'd say. So we need to introduce integration testing and system testing at the system level. So there are tools that can help us with the testing that we have. So this graph is to show that sort of as time goes on, we can write more tests, and the more tests we write and the more tests we pass, the more our confidence grows that our application is going to work as it's designed to. But there's only so much we can achieve because we have strict deadlines. Everyone's got sort of releases to get to, deadlines to meet. So we only have a certain amount of time. So how can we increase our confidence by increasing the amount of testing we can do to our application in the same time given to increase the confidence level that our application is going to work? Well, there are lots of different tools that can help us with this, but we're going to look at one in particular. So again, because we're all great developers, we're following Agile, we're testing, we're also going to follow the 12-factor app principles. And the one that I'm pointing at here in particular when it comes to testing is number 10. The dev prod parity. So what does this really mean? What does number 10 in the 12-factor apps mean? So the dev prod parity is all about keeping the development, the staging, and the production environments as similar as possible. Now, often there are sort of mostly 3 common issues that come into play which sort of prevent this from happening. So there's the time gap. The time gap refers to sort of the amount of time it takes you to actually write the code change and then to get that code change pushed into production. So that sort of time gap between the two can cause issues because there could be more changes in the code base, or the tools between when you make the change and when your change gets into production could be completely different. Then we've got the personnel gap. So the personnel gap, as you can guess, is a difference in the personnel handling each aspect. So you might have a developer writing the code locally, but a completely different ops guy actually going and deploying it, who might configure it completely differently. Then we've got the tools gap. So the tools gap you might be using one software stack locally in your dev environment, maybe because it's faster and it's more convenient, but you might be using a completely different software stack in production, maybe because it's more robust. But in that case, all of these different issues can create differences between your development, staging, and production environment, which prevents this dev prod parity. So this great quote here is from the 12-factor website, the 12-factor app website. So it says here, the 12-factor developer resists the urge to use different backing services between development and production, even when adapters theoretically abstract any differences in backing services. So even if you might be using adapters, there still could be issues between the two environments. So it's just best if you're able to use the same environment in development, staging, and production. And it stops excuses like this. Well, it works on my machine. If it works on your machine and you're using the same environment in development and production, it should work in production as well. So by keeping this dev prod parity, we're able to eliminate any potential issues that might occur through any of these different issues that I mentioned earlier, the personnel, the time, or the tools gap that I mentioned here. So we've got, to combat this, test containers were introduced. So test containers is a Java library that supports JUnit tests, providing lightweight, throwaway instances of common databases. And anything else that really runs in a Docker container. So it basically allows us to utilize Docker containers and sort of the idea of containerization within our tests. So as a result, we can write these self-contained integration tests that can depend on external resources like database or web browsers or messaging systems or messaging brokers. So it really allows us to create an environment that's much closer to production, much closer to the environment that we'd actually be using in real life. And it allows us to make these kinds of following tests easier. So data accessing layer integration tests, application integration tests, and UI acceptance tests. Now, taking test containers one step further, we have the open source project Microshed Testing. So Microshed Testing works with any Java EE, Jakarta EE, or MicroProfile runtime. So it's a great way of testing because, again, just like MicroProfile, it doesn't lock you in to a particular software or a particular vendor, because just like MicroProfile, you can use it with a variety of different vendors and different products. So what Microshed really gives you is it allows you to have this test containers API that controls the Docker network, and it can do basically simple orchestration of the containers inside. So it introduces these things called convenience libraries, which help you to interact with those containers. So like REST clients, for example. And it has JUnit extensions on top of that, which make it sort of nicer to use. So users can write their own test code on top of the Microshed Testing APIs. There's no extra config files. You just have to add the dependency into your POM file and create your Java code for testing. So essentially what you need to do, the steps that we're going to be making in this sort of, in the files and the classes we're going to be creating in this next lab, are that when we're using Microshed Testing, to use it effectively, we need to define the container we want to be testing. So where is my app running? We need to wait for the app container to be ready, inject the REST client, and that will drive requests on the running app container. So those will be HTTP requests to the container to test your application based on the Java code that you've written to test it. And then that will return back JSON so that you can then parse that into Java and do processing on it or whatever, or logs. So we're going to be using Microshed Testing because it can help us to really test our application in an environment that's as close to production as possible. Really trying to minimize the blockages or the prevention of trying to get to that dev prod parity. So really trying to follow the 12-factor app methodologies and test our application as close to production as possible. So our aims for Module 2 are to learn how to write integration tests for reactive Java applications, and to learn how to run the tests in true to production environments by using containers with Microshed Testing. So we're going to be using the same application again, so system and inventory, but this time just introducing our testing methodologies and our integration tests. So let's go check out Module 2. So now we're on to Module 2, Testing Reactive Java Microservices. Like I mentioned before, don't be worried if your previous history shows up in your terminal. Because you've logged into this environment, it will save your progress until you log out. So if you want to lose that progress, you can do if you want to log out and log back in. But it's fine because we have cleared out our environment and we have removed and deleted the sort of folders that we were using previously in lab number 1. So in this one, we're going to be using Microshed Testing, like I mentioned in the presentation. So it tests your containerized application from outside the container so that you're testing the exact same image that runs in production. So this paragraph here sort of sums it up really nicely in that tests sometimes pass during the development and testing stages of an application's lifecycle, but then fail in production because of differences between your development and production environments. While you can create mock objects and custom setups to minimize differences between environments, it's difficult to mimic a production system for an application that uses an external messaging system, like we are with Apache Kafka. Microshed Testing addresses this problem by enabling the testing of applications in the same Docker containers that you'll be using in production. As a result, your environment remains the same throughout the application's lifecycle, from development through testing and into production. So that's the importance of using something like Microshed Testing so that we can really aim for that dev prod parity. So let's get started. So if you haven't got the terminal window open already, you need to go to terminal and open a new terminal. Mine's already come up because I haven't logged out from the previous lab that we were doing. So let's just check we're in the right directory. PWD, yep, so I'm in home and project where I need to be. So we're just going to clone this repo and clone the code down. And then we're going to cd into that guide reactive, this time service testing directory. So now that we're in that, the first thing is we can try what we'll build. So if you head again into the finished directory, you'll see the finished application before we actually give it a go building it. So you can run the Maven command, download the correct OpenLiberty Docker image, navigate to the system directory, and you can verify the application using the Maven verify command to build the system service and run the integration tests. Now we're going to skip through this for the sake of time. If you'd like to have a go at this, feel free, but we're just going to go on ahead and go straight to sort of building it ourselves in the start directory. So we're going to cd into start. We don't need the // because we weren't in the finished directory. So we're just going to cd start. Let's just check I'm in the right directory. Yep, so I'm in the start directory. So the example reactive application consists of the system and inventory microservices. The system produces to the Kafka message broker and the inventory consumes. So again, the same application that we were using before. We're going to write integration tests to see how we can use the Kafka consumer and producer client APIs to test each service. Microshed Testing and Kafka test containers have already been included as required test dependencies in your Maven pom.xml files for the inventory services. So we don't need to include it in, we don't need to redo any of that. So we've got the system service directory, the inventory service directory, and the models directory. The models directory, which we haven't looked at yet, but we're going to look at here, contains the model class that defines the structure of the system load data that is used in the application. Run the following Maven goal to install the packaged models artifact to the local Maven repository so that it can be used later by the system and inventory services. So it's a fairly easy command. We're just going to copy and paste that in. So within this lab, we're going to be utilizing the OpenLiberty development mode, which is a Maven mode we can basically put OpenLiberty into, which we commonly refer to as dev mode. And within that, we can use Microshed Testing to run tests on an already running OpenLiberty server. So essentially, any changes we make to the underlying code will be automatically picked up, and the sort of application will be rebuilt automatically. So we don't have to keep stopping our application, saving the changes, restarting it. Dev mode will do that for us. So as you can see here, when you run OpenLiberty in dev mode, the server listens for file changes and automatically recompiles and deploys your updates whenever you save a new change. So we're going to run this command to run, now that we've completed that Maven command, we're going to be running in dev mode. So for those of you who haven't tried dev mode before, this will be an exciting new time for you to try dev mode. So after we see this message, our application server in dev mode is ready. So we'll just wait for that to appear. So dev mode holds our command line to listen for file changes. If we need to do any other commands, which we will need to do, we're going to have to open a new command line to continue. So we're going to do terminal. We're going to do split terminal so we can see both. This way I can post commands into here whilst also looking at what's happening here. If you don't want to split the terminal, you can always just do terminal, new terminal. And once this shows that we've finished, here we go. Then I will just sort of shrink this back down so you can see my commands properly in this one. Might just take a little bit of time. Cool, so once we press enter, we automatically run the tests. Cool, we've got no test to run at the moment because we haven't built our integration tests really. So now that we've got this message here, you can see that we're ready to get going. So I'm just going to shrink this one back down again so that we have my one here. In fact, I'm just going to create a new terminal. There we go. So we need to now create the tests. So we need to create a class to externalize our container configuration. So we're going to create this class app container config. So copy and paste the command into there. Oh, that's because I haven't CD'd into the right directory. So I need to CD into guide, MicroProfile. We don't want the reactive messaging one. Let's see what we've got in our folder. CD into guide, reactive service testing. And then we're going to CD into start. Fantastic. So now we should be in the correct location. So let's try this command again. So make sure you CD into the correct location because we have opened a new terminal. Oh, just check this out. Just double check. Because we haven't CD'd into system. So make sure you CD into system as well. Don't make my mistake. There we go. Fantastic. So now it's worked. So let's head back to step 5. So now that we created this app container config class, what we need to do is we need to head on into that. So we'll go into File, Open, and we want to go to the testing service, into Start, back into System, SLC. This time we want to go into Test though, not Main. So make sure you go into Test because we're testing. Java, IT, IO, Open Liberty, Guides, and System. And there's our app container config.java class we just created. So we'll open that up. It'll be blank and empty because we haven't, we've only just made it. We haven't implemented anything yet. So let's copy and paste that in and remember to save. So we can use the same application containers across multiple tests. So you can see here the app container annotation we're using denotes an application container that is started up and used in the tests. So 2 containers are used for testing the system service, the system container, which you build, and the Kafka container, which receives messages from the system service. So you can see here the Kafka container here, and you can see this is the application container here. So that's all within our app container config.java. The depends on method that we're utilizing within this application, so right here, notice that it says depends on Kafka. So the depends on method specifies that the system service container must wait until the Kafka container is ready before it can start. Because there's no point testing our system if we can't receive and send to Kafka. So, testing your containers. Now we can start writing the tests that use the configured containers. So we need to create the system service IT class. So let's copy and paste this command again into the terminal. There we are. And then we need to open that up. So File, Open, Guide Reactive Service Testing, again Start. We need to go to System again and then to SLC. Remember it's test, not main. So test, Java, IT, IO, Open Liberty, Guides, System, and then you can see the system service IT.java file there. So again, blank, so we need to copy and paste into it. So let's copy and paste all of this in. So the test uses the Kafka Consumer Client API and is configured by using the Kafka Consumer config annotation. The consumer client is configured to consume messages from the system load topic in the Kafka container. So remember we were using this topic before in our properties file that we edited in lab 1. To learn more about Kafka APIs, you can check out the official Kafka documentation. To consume messages from a stream, the messages need to be deserialized from bytes. Now remember when we set up those configuration, those properties files before, I pointed out that there were some deserialization tools in there. So it's configured so a custom deserializer is provided for you but Kafka has its own default deserializer. The deserializer is configured to the consumer value deserializer and is implemented in the system load class. The running system service container produces messages to the system load Kafka topic, as denoted by the test CPU status method. Test method polls a record from Kafka every 3 seconds until the timeout limit. It then verifies that the record polled matches the expected record. So let's take a look. So we've got, please print out what's polled. And we've got here, we're using this method, test CPU status, to test that the system service is producing messages to Kafka. And this test method is sort of polling from Kafka every 3 seconds. And then once it's polled, just printing out what it gets in terms of the records from Kafka. Now we can press enter in our terminal because we're in Liberty dev mode, and we should see the following. Oh, we haven't gone into Liberty in our other terminal, and we should see the following output once we've run it. Let's have a look. So it might take a little bit of time for the tests to run, but once you've run them, you should see something similar like this. So it says tests run 1, failure 0, error 0, skipped 0. Again, if you want to run them again, you can just click enter. It should run a bit quicker this time because you've already run it once before. So let's see if this works again. Again, as I said, it might take a little bit of time just because it is testing inside a container. So once we've finished running the test, we're going to stop the OpenLiberty server by typing Q in the shell session where we ran the server. So again, you can see this test ran absolutely fine. So we're going to press Q and enter so that we can exit from Liberty Dev mode. If you aren't running Liberty Dev mode, you can use the Maven command, Maven verify, and you should see the following output the same as before. So now we're going to navigate into the inventory directory. So let's copy this command in. So cd into the inventory. This is because the inventory service is tested in the same way as the system service. The only difference this time is that the inventory service consumes messages rather than producing them to Kafka. So this time our tests don't need to test whether it's producing to Kafka, but now need to check that it's consuming from Kafka correctly. So the app container config class is provided, and it's configured in the same way as it was for the system service. So that was this file that we edited first. With the different containers that we were using. So it's configured in exactly the same way. We don't need to configure this one because it's been configured for us. The two containers that are configured for use in the inventory service integration test are the Kafka and inventory containers. So testing your containers. As we did with the system service, run OpenLiberty Dev mode to listen for file changes. So we're going to rerun OpenLiberty Dev mode in this original terminal that we had open. So once we've got OpenLiberty Dev mode up and running, we can create our integration tests. So we need to open up a new terminal. I'm just going to use the same terminal I was using previously. So I'm going to head back to my other terminal whilst that's setting up. And in this terminal, let's just check where we are. So we're still inside the system directory. So I'm going to cd out of that. And now I'm going to cd into the inventory directory. Fabulous. So now I'm in the inventory directory where we need to be. And then we're going to paste this second command to create that inventory service it.java file that we need. So now we're going to go to File, Open, Guide Reactive, Start, Inventory. Then we're going to go to src, Test, Java, IT, IO, OpenLiberty, Guides, Inventory, and Inventory Service IT. So this does say system here, but we all get this changed by the time you guys have a go with it. But it should be inventory here instead. So now that we've got this open, what we're going to do is we're going to copy and paste what we need to into this file. So let's save that. So essentially here, the Kafka producer config annotation configures the producer to use the custom serializer provided by the annotation, which doesn't include a topic that the client produces messages to, because it has the flexibility to produce messages to any topic. In this example, we're configuring it to produce messages to the system load topic. So the test CPU usage test message produces a message to Kafka and then verifies that response from the inventory service matches what is expected. So in this case, we're trying to prove via testing that we're able to consume correctly from Kafka the events that are being published there. So you can see here, here's the test CPU usage test that we're doing. And what we're doing is we're trying to assert that the response that we put is equal to the one that we're expecting. So the REST client annotation injects a REST client proxy of the inventory resource class, which allows HTTP requests to be made to the running application. So if we go back to our Liberty Dev Mode terminal and we hit enter, it should start our tests for us. Again, this might take a little while, but it will start running our tests. And when it's finished, we should see an output similar to the following here, showing us that one test has run and that we have no failures, which is hopefully what we're hoping for. So we'll just leave this to run for a little while. Fantastic. So test run 1, failure 0, error 0, skip 0. Exactly what we want to see, and the integration tests are finished. So now we're going to quit OpenLibc Dev mode by doing that Q and enter. As we said, but similar to how we did with system, if you're not running in dev mode, you can do Maven verify, and you should also see a similar output to the one here. Let's continue. So now that we've finished our integration testing, we've been able to show you that by using Microshed testing, we've been able to run in an environment as close to production as possible, and we've been able to show how we can test that our services are able to correctly interact with our messaging broker that we're using, that we would be using in production as well as in development here. So now that we've finished this testing lab, we're going to clean up again. So we want to use the cleanup scripts provided to remove those folders and all that code. Fantastic. So now we're done. We're going to move on to a short coffee break. I'm just going to give you a few minutes just to get up, stretch your legs, grab a coffee, grab a drink, head to the toilet, and then we'll be back in about 5 minutes to restart the next lab. So now that we've finished that short coffee break, we're going to move on to module number 3. So in this case, we're going to be looking at how we acknowledge messages using MicroProfile Reactive Messaging. So to ensure that no messages are lost in the event of a system failure, most messaging systems differentiate between a message being delivered to a system and the processing of that message by the system being complete. So if the system goes down, any messages which have been sent but not completed can then be sent again. So in this case, reactive messaging applications implement this sort of technique using message acknowledgements. So when all the processing of the message has been completed, so that it wouldn't need to be reprocessed in the event of system failure, it must be acknowledged. So connectors in this case can communicate back to the messaging system which sent the message that it has been fully processed. You can see here from the diagram at the bottom. There are different types of acknowledgement strategies that you can utilize within reactive messaging. So there's manual or there's automatic. And in automatic, you can have either pre-processing or post-processing. But we'll go through this in a bit more detail in the lab itself. So our aims for this module are to learn how to acknowledge messages by using MicroProfile Reactive Messaging. We're going to explore the acknowledgement strategies that are available with MicroProfile Reactive Messaging, like I mentioned, and we're going to learn how to implement our own manual acknowledgement strategy. So in this case, our architecture diagram's gone a little bit more complex over here. So we've actually broken down the different sort of communication that's going between the different systems. And this time we're using an at-put request, you can see at the bottom here. So let's get on with looking at module number 3. So let's get started with module number 3. So we're back to the SNL environment. You just need to click on from the sort of the home page. You just need to go ahead and click on that module 3. We're looking at acknowledging messages using MicroProfile Reactive Messaging. So let's head straight on into the code itself. So we need to make sure that we are in the correct directory. So let's pwd. Yep, so I'm in home project, which is the correct directory. We're going to do a git clone of all of the code we need. So let's take a look. And now we're going to cd into that guide MicroProfile. This time, reactive messaging acknowledgement is the directory we need. Just like from before, the finished directory in the root of this guide contains the finished application, if you would like to take a look at that. But we're going to look at the start directory so we can code it ourselves. So, choosing an acknowledgement strategy. Like I mentioned, there are different acknowledgement strategies you can choose when you're using reactive messaging. So, as I said before, messages must be acknowledged in reactive applications. Messages are either acknowledged explicitly or messages are acknowledged implicitly by MicroProfile Reactive Messaging. Acknowledgement for incoming messages is controlled by the @acknowledgement annotation in MicroProfile Reactive Messaging. So that @acknowledgement annotation is quite important. If the @acknowledgement annotation isn't explicitly defined, then the default acknowledgement strategy applies, which depends on the method's signature. Only methods that receive incoming messages and are annotated with the @incoming annotation must acknowledge messages. So only microservices or methods that consume, so have an @incoming annotation, need to care about these acknowledgements. Methods that are annotated with the @outgoing annotation do not need to acknowledge messages because messages aren't being received. And MicroProfile Reactive Messaging only requires that received messages are acknowledged. So we only really care about the methods or the microservices within our system with an @incoming annotation. So almost all of the methods in this application that require message acknowledgement are assigned the post-processing strategy by default. If the acknowledgement strategy is set to post-processing, then MicroProfile Reactive Messaging acknowledges the message based on whether the annotated method admits data. So if the method admits data, the incoming message is acknowledged after the outgoing message is acknowledged. If the method doesn't emit data, so in other words, it just consumes, but it doesn't do any processing and resubmit a new message, the incoming message is acknowledged after the method or processing completes. So basically, if you have a method or microservices that's taking in some of that data, doing some sort of processing and posting to a new channel, so producing as well, so it's a processor because it's doing both incoming and outgoing, then it's only going to acknowledge the message after the outgoing message is acknowledged, because that means you've finished the processing and you've sent the next message along. But if it isn't a processor and instead it's just a consumer method and it's just using the incoming, then the incoming message is acknowledged after the method or processing completes. So it's just basically checking you finish the whole completion of everything that needs to be processed to do with the data in that message. Then you can continue. And as we mentioned in the presentation, this is to make sure that if the system was to fail and go down, that you'd be able to pick back up again and know that you still had to process that message. So it's important that the methods use post-processing strategy because it fulfills the requirement that a message isn't acknowledged until after the message is fully processed. This processing strategy is beneficial in situations where messages must reliably not get lost, which is important in reactive applications because we want to be resilient and we want to be responsive to events and not lose events because our system failed. When the post-processing acknowledgement strategy can't be used, the manual strategy can be used to fulfill the same requirement. In situations where message acknowledgement reliability isn't important and losing messages is acceptable, the pre-processing strategy might be appropriate. So as I mentioned before, there's manual or there's automatic. And automatic can be broken down into post-processing or pre-processing. If you don't care about losing messages and you're not really bothered about acknowledgement reliability, you can use pre-processing. But most reactive applications do care about losing messages, and so in that case they need to use post-processing acknowledgement strategies. If you can't use the automatic post-processing strategy, then you'll need to opt for the manual strategy. So the only method in the guide that doesn't default to the post-processing strategy, in this case, is the send property method in the system microservice. The send property method receives property requests for the inventory service. For each property request, if the property that's being requested is valid, then the method returns a property response with the value of the property. However, if the requested property doesn't exist, the request is ignored and no property response is returned. A key difference exists when a property response is returned and when a property response isn't returned. In the case where a property response is returned, the request doesn't finish processing until the response is sent and safely stored by the Kafka broker. Only then is the incoming message acknowledged. However, in the case where the requested property doesn't exist and a property response isn't returned, the method finishes processing the request message, so the message must be acknowledged immediately. This case where a message either needs to be acknowledged immediately or sometime later is one of the situations where the manual acknowledgement strategy would be beneficial. So let's take a closer look at this. So let's navigate into the start directory. Fantastic. So we're going to update the system service.send property method to use the manual acknowledgement strategy, which fits the method processing requirements better than the pre-processing strategy. So we're going to replace the system service class. To do that, we need to open it. So let's go to File, Open. This time we're going to go to the acknowledgement one, because that's the guide we're in. Nope, we're not in the guide, sorry. We are in... which one are we in now? Now I'm confused. Yep, we are in the acknowledgement one. So let's take a look at that. So go into Start, System, SRC, Main, Java, IO, Open Liberty, Guides, System, and then we're going to go into the system service.java class. So this time it has got data in because that's the way we created this. We didn't create the file just now. We had no touch command. So what we need to do now is select all of this, delete it, and copy what we have here in the instructions over into the file and paste that in and save it. So the send property method needs to manually acknowledge the incoming message. So it's annotated with the acknowledgement strategy manual. This is the important bit, manual. So let's take a look for that now. So we've got acknowledgement here, acknowledgement strategy manual. So this annotation sets the method up to expect an incoming message, hence why we've got the incoming annotation here. To meet the requirements of acknowledgement, the method parameter is updated to receive and return a message of type string, rather than just a string. So we can see here, property get message, and so instead of just getting a string, we're now getting a message that contains a string. Then the message payload is extracted and checked for validity. One of the following outcomes occurs. So if the system property isn't valid, the system acknowledges the incoming message and returns an empty reactive stream. So we can see here, if the property name is null or is empty, or the property value is unknown, then we need to send a warning to say that it wasn't in there, and we need to return this as soon as we can with an empty reactive streams. If the system property is valid, so you can see here the alternative, then Then the method creates a message with the value of the requested system property and sends it to the proper channel. The method acknowledges the incoming message only after the sent message is acknowledged. So you can see here that we only acknowledge once the sent message has been acknowledged. So you can see here where we had the PowerPoint presentation with the diagrams going across, you can see how the acknowledgement passes through the connectors back to the methods. So waiting for a message to be acknowledged. The inventory service contains an endpoint that accepts put requests. When a put request that contains a system property is made to the inventory service sends a message to the system service. The message from the inventory service requests the value of the system property from the system service. Currently, a 200 response code is returned without confirming whether the sent message was acknowledged. Replace the inventory service to return a 200 response only after the outgoing message is acknowledged. So in this case, where we're accepting a put request that contains a system property, so basically we need to basically introduce that acknowledgement. So what we need to do is open up the inventory resource class. So we're going to acknowledgement again, start, this time inventory, src, main, java, io, open liberty, guides, inventory, and there's our inventory resource class that we need to edit. Again, this has stuff in, so we need to get rid of all of that and replace it with what we've got in the instructions. Scroll all the way down to the bottom of that, copy, paste, and save. So the send property name method is updated to return a message again, instead of just a string. So let's take a look at the send property method. So where am I looking now? Oh, let's go search for it. Here it is, so send property name. So we can see here that the send property name is getting a method instead of just a string. This return type allows the method to set a callback that runs after the outgoing message is acknowledged. In addition to updating the send property name method, the property name emitter variable is updated to send a message type. The updated system property method now returns a completion stage object wrapped around a response type. This return type allows for a response object to be returned after the outgoing message is acknowledged. The outgoing message is created with the requested property name as the payload and an acknowledgement callback to execute an action after the message is acknowledged. The method creates a completable future variable that returns a 200 response code after the variable is completed in the callback function. So you can see here that we're not calling the 200 response until after we get the acknowledgement back in return. So this is the important change that we've made to this system to make sure all the processing is complete before we return that 200 response code in the callback function. So building and running the application. So now we need to build and run it using our Maven commands. So if we go back to the terminal and paste in these commands, so let's do that, and then let's do a Maven package. And then again, we need to do similar to what we did before. We need to make sure we've got the latest version of the Open Liberty Docker image. So let's do that second Maven command, Maven package. Wait for that to complete. Tab, and then we will make sure we've got the right version of the Open Liberty Docker image. We've got several versions of Open Liberty's Docker image up on Docker Hub. So if you want to check out different sizes, varying sort of purposes, so check out our page on Docker Hub if you want to check out what Docker images we have available for Open Liberty. So let's run the following commands to containerize the microservices. So let's do this Docker build for the system microservice, and then let's do the same thing for the inventory microservice. Now we want to use the provided script to get them up and running again. So again, this starts containers for Kafka, Zookeeper, and the microservices of the project to make sure they're all up and running for us to use. And then we want to test our application to test that it still works after all the changes we've made. Great, so our containers have started. So we can curl the system. Again, it might take a little bit of time just for the system to get properly up and running. So we'll just give it a few seconds and then I'll hit that curl command to see. Yep, so it's empty at the moment, you can see here, because our containers haven't quite started up and they're not quite ready for me to get the system load yet. So the system service is still sending messages to the inventory service every 15 seconds, but the inventory service only processes and acknowledges each incoming messages once that processing is complete. So only acknowledges once the process is complete on it, ensuring that no system message is lost, which is really important for reactive applications. So let's check this is working. Yep, so we've got our system load data back again. So make a put request to this to add the value of a particular system. If you've got more systems than just one running, we've only got one running, then you can do the following curl command to get that. Cool, and then as I said, same as before, you can re-input the same curl command if you'd like to see that system load change over time. So we can actually do this curl command. Cool, so if we do this curl command here, then what we're doing here is we're now actually asking to make the OS name of the system available when we run that same command. So the URL adds the OS name system property for your system. The inventory service sends a message that contains the requested system property to the system service. The inventory service then waits until the message is acknowledged before it sends a response back. So we should see the following output. We see the following output because we've done the processing, we've had the acknowledgement, and so we can put this response back. So the previous example response is confirmation that the sent request message was acknowledged. So now let's revisit that curl command, and this time we see the OS name Linux in there in addition to what we saw before. Fab. So now we need to tear down our environment again because this is the end of module 3. So what we've been able to do is we've been able to sort of introduce acknowledgement to make sure that all the processing is complete before we continue with anything, to make sure that if the service or the system was to go down, that we'd be able to start up again without losing any messages and any important data that we might need. And again, just like before, we need to clear up our environment by directing those directories in that code. And that's the end of module 3. So now we'll move on to module number 4, our last and final module. So our final module of this workshop is going to be looking at how we can integrate with RESTful services into our reactive system using MicroProfile Reactive Messaging. And that might be necessary because there might be, let's say, parts of your application that are more legacy code, that might be RESTful services that you can't turn into a reactive microservice right now, or you might be interacting with another service from, let's say, a third-party company or external that, again, has to be interacted with in a RESTful manner. So for this module, we're basically going to be looking at how we bridge the gap between reactive systems and RESTful Java microservices using the RxJava library. We're going to learn how to modify microservices in an application so that when a user hits a RESTful endpoint, the microservice is able to generate producer events. So let's take a look at our last and final module, module number 4. So let's begin our final module of this workshop, which is module number 4, integrating RESTful services with a reactive system. So we'll be integrating a RESTful Java microservice with the reactive system we've been using throughout these labs. So in this lab, we're going to be updating the inventory microservice. So this time it's going to subscribe to a put request response. This put request response accepts a specific system property in the request body, queries that system property on the system microservice, and provides the response. You will also update the system microservice to handle receiving and sending events that are produced by the new endpoint. We're going to be configuring new channels to handle these events that are sent and received by the new endpoint, so that we can learn more about how we can interact with a RESTful endpoint in this regard. So let's get started. I've opened up a new terminal. Let's just check we're in the right place once more. So yep, in that home project directory, and let's clone what we need to clone down. Great, so we've got it in, and I've just CD'd into Guide MicroProfile Reactive Messaging REST integration this time. Again, we're going to be looking at the start directory. So we need to CD into start. So the inventory microservice records and stores the average system load information from all of the connected system microservices. In this case, we've only got one running, but again, if you want to push yourself, feel free to get more than one running and take a look at what happens when you do. However, the inventory microservice does not contain an accessible REST endpoint to control the sending or receiving of reactive messages. We're going to add the /data endpoint, RESTful endpoint, to the inventory service by replacing the inventory resource class with an updated version. So we need to open that up. So we need to go to File. We're going to REST integration this time. We need to go into the Start, and then Inventory, and then src, main, Java, IO, Open Liberty, Guides, Inventory, and there we have the inventory resource Java class. So as we said, we need to replace it. So we need to select all of this code, delete it, and then copy what we have in the instructions here. So if you scroll all the way down, it's quite a long file now. Copy that, paste it in, and save. So the update system property method creates the data endpoint. So let's take a look at the update system property method. Here it is. So update system property method. And this is the one that creates the /data endpoint. So that's the one we want to look at. That accepts put requests with a system property name in the request body. The property name emitter variable is an Rx Java emitter interface. So the property name emitter interface. So here it is, property name emitter, that sends the property name request to the event stream, which is Apache Kafka in this case. The send property name method, which I believe is further down. Let's just have a look. Yep, send property name, the last method here, contains the flowable create RxJava method, which associates the emitter to a publisher that is responsible for publishing events to the event stream. The publisher in this example is then connected to the @outgoing request system property channel, which you will configure later on in this guide. MicroProfile Reactive Messaging takes care of assigning the publisher to the channel. So we've got the outgoing here and the request system property. The flowable.create method also allows the configuration of a back pressure strategy object. Like we mentioned before, the observable method that was available in, and is still available in RxJava, but was the only available one in RxJava 1.0, then got introduced in RxJava 2.0, was flowable because it enabled this back pressure to be added. So this flowable.create method allows the configuration of this back pressure strategy, which controls what the publisher does if the admitted event can't be consumed by the subscriber. So maybe the subscriber's gone down temporarily and it can't take any events right now, in which case we need to have some sort of feedback mechanism. That's where that back pressure strategy comes in. Like we mentioned at the very start of this workshop, one of those important reactive architecture patterns that we utilize. In this example, the publisher uses the backpressure strategy.buffer strategy, which is one of the strategies you can select. With this strategy, the publisher can buffer events until the subscriber can then consume them again. When the inventory service receives a request, it adds the system property name from the request body to the property name emitter flowable emitter interface. The property name sent to the emitter is then sent to the publisher. The publisher sends the event to the event channel by using the configured backpressure strategy object when necessary. So we're going to add an event processor to a reactive service now. So the system microservice is the producer of the messages that are published to the Kafka messaging system as a stream of events. Still, every 15 seconds, the system microservice publishes events that contain its calculation of the average system load, which is its CPU usage, for the last minute. We're going to replace the system service class to add message processing of the system property request from the inventory microservice that we just coded, and we're going to publish it to the Kafka messaging system. So now we need to open up our system service class. So we're going to get into REST integration, start, system, src, main, Java, IO, Open Liberty guides, system, and then there's our system service.java class. So open that up, and again we need to replace the whole thing. So we need to copy, select it all, delete, and then copy from the instructions on the left hand side. And always remember to save. So we've got a new method in here now called sendProperty, which receives a system property name from the inventory microservice over the @incoming channel. So we can see here that we've got sendProperty, there's the method, and we've got the @incoming property request channel. The method calculates the requested property in real time and publishes it back to Kafka over the @outgoing, you can see here, property response channel. So in this case, our system service is acting as a processor because it's taking that request in, doing some sort of processing, and sending a new method out, new message out. In this scenario, the send property method acts as a processor. Next, you'll configure the channels you need. So now we need to configure them. Just like we did in the first guide, we now need to configure the channels within the properties classes that we created so that we can add these new channels property requesting. So the system and inventory microservices each have a config file, which we edited in the first lab. So these properties include the names of channels, the topics in the Kafka messaging system, and the associated message serializers and deserializers. To complete the message loop created in the previous sections, we now need to add 4 channels to these configuration files. So we need to go and edit the inventory configuration file first. So we'll go open, guide REST integration, start, and then we're going to go to inventory, src, main. Then we're going to go to resources, metainf, and find that config properties file. I'm going to open that up. And again, we need to replace what's inside here. So we're going to select it all, delete, and copy what's in the instructions here, paste it back in and save. Oh, paste it back in and save. There we go. So now we've added in 2 new channels that remove the requested messages, the requested messages between the system and inventory microservices. So you can see here the add system property topic, and then below it the request system property topic, which weren't there before. Before we only had the system load topic that we were using previously. So we've added in these 2 new channels. The inventory microservice property file has these 2 new channels. The request system property, so this one down at the bottom, this channel handles sending the system property request, and this add system property topic handles receiving the system property response. We now need to go into the system properties file and change that as well. So open, REST integration, start, go into system, then go into src, main, resources, metainf, and microprofile config properties. So now we're inside the system config properties. So again, select it all, and then delete, and then we're going to go and add in what we have on the left-hand side here and save. Again, you can see here that previously we only had the system load topic channel. Now we've got the add system property topic and the request system property topic. So you can see if you compare the two, this one's the incoming, which is the add system property. This one's the outgoing, whereas this one is the outgoing for the add system property and the incoming, which makes sense because they match up together. So we've replaced it. So now we've got 2 new channels. In this case, the property request channel handles receiving the property request, and the property response channel handles sending the property response. So now we're going to build and run our application like we've been doing before. So copy in these Maven commands to get our application up and running. So let's copy and paste that first one, wait for it to complete. There we go, build success, fantastic. So now we're going to do a Maven package. And again, we're just going to make sure we've got the right version of the Docker image by copying this Docker command here. Wait for this to complete. We should see a build success, fantastic. Then we'll get the Docker pull going. And then we're going to containerize both of our microservices, system and inventory. Fantastic. And again, we're going to get Kafka, Zookeeper and our microservice containers up and running so we can test this application. Similarly to before, we're going to use the same curl command to see if we can get our inventory system data back. So we'll see if we can get that system load back from the system service through to Kafka, through to the inventory, and we're just pulling that down so we can see it. So it's completed, but again, this might take a little bit of time. You're probably used to this by now. Give it a few minutes before you do this curl command, just to make sure your application is up and running and has at least done one poll to Kafka to get that data. Yep, so not quite ready yet because that box is empty. Let's try again. Fantastic, and there's our system load. So now what we're going to do is, similarly to what we did in module number 3, we're going to make a put request onto this URL to add the value of a particular system property to the set of existing properties. So we're going to add this OS name to the system properties. So let's copy and paste that command in. And that request successful for the OS name property confirms that we're ready to go. So in this example, the put request with the OS name system property in the request body adds the system property for your system. The system service is available, so the request to the service is successful and returns a 200 response code. But remember, we haven't included the acknowledgement here, so this is just the 200 response code before we've done all of that work with the acknowledgement to make sure that that processing happened. So you can see how these guides start to sort of interplay with each other. So let's have a look at the curl command. And yep, we can see the OS name Linux now, so that successfully worked. So as I said before, you can run multiple instances of that system microservice if you do want to see more than one system show up and if you want to have a play around with sort of controlling different system services within it. But you will need this group ID if you do want to use it as an environment variable. Cool, so that's us completed our final lab of integrating with RESTful services. So what we just need to do is the last few steps of tearing down the environment and cleaning up our environment. So once those containers have come down, we'll just do those last few cleanup commands and head back to the presentation for some useful resources and a brief catch-up. So hopefully what this workshop has sort of taken you through in a hands-on manner and with some theory at the start there is it's helped you to understand how you can create a reactive Java microservices-based system or application using MicroProfile Reactive Messaging. It's helped to show you how to introduce true to production testing for reactive Java microservices. It's shown you how to successfully introduce acknowledgement strategies, both manual and automatic, when using MicroProfile Reactive Messaging, and how to integrate a RESTful service with your reactive system. So if you'd like a little bit more information on reactive systems or just want something to refer back to, then check out this free O'Reilly book that I authored with a colleague of mine called Reactive Systems Explained. It's a short, about 30-page book that just helps you to sort of summarize and have a reference back to what reactive systems are, when to use them, and how to build them. So thanks very much for attending this workshop. If you do want to check out some more reactive resources after this session, then I'd recommend some of the links below. So we've got there the Reactive Manifesto if you want to check that out in more detail. We've got some resources like getting started with the reactive, defining reactive, and reactive with MicroProfile. If you'd like some sort of summary articles that we've written on IBM Developer around the subjects we've gone through in this workshop. Or if you want to try something different, because we've used a lot of OpenLibty in this session, if you want to try reactive Java with Quarkus, then check out that link that I've given you there. On the right-hand side, I've given you some links to the reactive frameworks and toolkits that we mentioned, like RxJava, MicroProfile Reactive Messaging, Vertex, Project Reactor, and Akka. And if you want to keep up with our Java news, then check out our Java newsletter via the newsletter links here, which you can sign up for sort of a monthly update of what's new in the world of Java. And you can check out our IBM Cloud resource there as well. Thanks very much for joining. If you do have any further questions that I haven't answered whilst going through this lab, then do feel free to ping me on Twitter. My Twitter handle's at the top there. So my name's Grace Jansen, and it's been a pleasure doing this workshop with you today. I hope you enjoy the rest of J4K.